to look at the different layers of the Earth and plate tectonics, um, and just basically what causes the plates to move and how the crust is set up. So I actually won't be surprised if this is a very long video, but we'll see how it goes. Structure of the Earth, I really like this background that I have over here because it shows you all the different layers of the Earth. You can see the crust is kind of like a shell around containing the whole thing. The mantle, that's the thickest part of the Earth. You've got the outer core over here containing the inner core, and that's kind of like cup or something. Okay, there we go. So this is a topic in geomorphology. So I always like to take a minute to explain what that actually means. And geomorphology is when we study the the shape of the earth or the things that influence how the earth is formed or shaped, the different features of the so geomorphology is anything that is physically earth. So we look at right now we're going to look a bit about the structure of the earth. If you're looking at geology, that will also be part of this. We look at fluvial geomorphology. So when we did the section on rivers, that is a type of geomorphology because rivers are okay. So anything that looks at the shape of the earth or the landscape, that is geomorphology. We are going to focus on unpacking the diagram. Cute little wedge that is a cutout of the earth and how it is layered from the outside. You guys remember to make your coffee? Have coffee. I must admit, I had way too much coffee during this exam period. My normal like one, maybe 2 cups a day went up to 3, possibly on some days. Yeah, we don't confess to coffee we have during exam time. So I want to start by talking about the lithosphere. The lithosphere, that is basically the sphere of rock. So that is the crust, it's the outer layer, and it's also a very top little part of the mantle, but it's basically the solid part. So you can see over there, so you've got the parts that are indicated black, layer of brown, that is all of the rock, that is all quite solid, that is all the lithosphere. So it's the uppermost layer. Okay, then we're not going to unpack every single one of these layers because it gets very complicated, especially around here. We're mostly just going to be looking at crust and the mantle. So we're sticking to our foundations right now. Then the mantle. The mantle is the thickest part of the earth or cross section of the earth. And I'll get through all of the characteristics still. Then outer core is also still liquidy and inner core is solid. Let's get to crust. This is where we live. That thin little layer in. Okay, so the crust, we have continental crust and we have oceanic crust. Continental crust, that is the physical land that we are living on. Okay, so continental crust is actually fairly thick compared to oceanic crust. So now, don't get me wrong, it's not thick compared to the whole of the Earth, with the mantle and the outer core is dense. But when we compare the two different types of crust, so that's about it depends on what sources you find. Some sources said 20 to 70 kilometers. One textbook I found was like 70 or 40 to 70. It all varies. It's an approximate. Obviously it depends on how the earth is structured in that particular part, kind of mountains have or kind of cave. So it's a ballpark of 35 to 70. It is less dense oceanic crust that is important. So what that means is that it would float on top of oceanic crust. oceanic crust would dip below the continental crust because the continental is lighter and less dense. Go to the top. It is also older than the oceanic crust. So oceanic crust is more likely to be formed and then destroyed throughout the whole rock cycle. We'll touch on that a little bit. Um, that means that the continental crust is usually the oldest. I do think that fold mountain rocks that. Okay, so that brings us to oceanic crust is a lot thinner, and because it's thinner, it is more packed as these two types of crust are made of different elements and rocks in topology. I tried to find the information on that, but I couldn't really sift through right now. I'll happily do that in another video, maybe when rock cycle, it's exactly what types of crust, but there are different types of rock in crust. Um, so the oceanic crust is thinner and a lot denser. So it would be more likely to sink than continental crust. You can think of the continental crust as being light and thick. You see the crust there, kind of. Um, so thinner, denser, it is also a lot younger. It tends to be created and destroyed a lot quicker than continental. Okay, I think we have that basically covered. Then we get to the mantle. So the mantle is a very thick part of the earth. Um, I did try to find out if this 2,900 kilometers depth, thickness. So let's go back to that other diagram. I'll show you what I mean. So here you can see the bracket. It starts from about there. It looks like it's excluding the crust and it goes to the bottom of the mantle. And I know that is labeled as the mantle, but I think that that's what the 2,900 kilometers is representing. But I'm also not sure if that's just the total depth. To be fair, the crust is at most 100 kilometers thick. So if I'm reading it wrong, it's either 2,900 or 2,800. I think we can forgive either way. So it's about 2,900. Okay, and then that is molten. It is liquid. So what is swirling around in there is referred to as magma. So this is completely melted molten rock, and it is moving just like any liquid. We will still look at the currents that form from it, but it's needless to say that this is very hot, about 3,000 degrees Celsius. Definitely hot. Okay, and it is denser than the crust. I need to state this because I have had a student ask me, how does the magma in the mantle not just break through the crust? Like, how is the crust strong enough to contain the mantle? And that's not quite how it works. It's that the mantle is denser. The crust is floating on top of it. You can kind of think of it like ice on water. Crust is floating on top of the mantle. It's not really like containing it. It's just chilling on top. We have to think about it that way. A few kilometers under your thousands and thousands of bubbling magma. Good morning! Welcome back! How are you? Oh wait, good morning. It's afternoon for me, but I assume it's morning for you. Hmm. Haven't seen you in a minute. Okay, so yes, denser than the crust. Oh, is it afternoon for you too? Okay, great. Yeah, I know that I'm streaming quite a bit later than I normally would have. I kind of lost track of time prepping. Okay, so now we're going to take a look at the outer core. So we have outer core and we have inner core. I quite like this diagram because there is the crust over there, there is the mantle, and this is the one that we're going to look at. That is the outer core right there. Okay, so the outer core is about 2,100 kilometers thick. This time I was actually certain that that was thickness and not depth. Okay, 2,100 thick, and it is also thin, but it's not as liquidy and as molten as mantle. But it also it can move. There is some it is significantly hotter. It is the heat source of the mantle. So you can kind of see that in this picture as well, how red it is right there. It's radiating that mantle. I probably shouldn't have radiating. That's not the correct form of heat. We'll worry about types of heat. Okay, that is consists of mostly iron and nickel. So when we looked at the mantle, that was molten rock, and this is metal. And then finally, we get the inner core. The inner core, I did check, this 1,250 kilometers, that is the radius. So it's not that it's 1,200 kilometers throughout the entire core. It's just to the center, the radius. So you can double that before you get the whole diameter. Okay, and that core is solid metal. So it will also consist of iron and nickel. Might actually just iron now that I'm thinking about it, but it's definitely solid. And the reason why it's molten is because it's under too much pressure. So you can think about it like those diving tanks, those like tanks that the deep sea divers would do, and they have the nitrogen and the oxygen, everything inside the tank. The those gases are not in gaseous state; they're in liquid state. But because they're in so much pressure inside that tank, they stay in a liquid state. And it's the same thing with this metal. It is warm enough for the metal to melt, but it doesn't have enough space to do that. Okay, and when we're talking about the actual heat, the core, we expect the inner core to be about 5,000 degrees Celsius. And for context, I think the surface of the sun is about 5,500 degrees. So that's quite close to the surface of. In other words, it's burn yourself. Don't go there. There's other stuff you guys are interested in. I'm more than happy to take some of that. So I made this just as a summary. So this was actually a printout for my student. A summary of the different layers of Earth. So we have the oceanic crust that is thin. You can see I've labeled that as blue. I didn't know that oceanic was water. We have the continental crust that's around 35 to 70 kilometers thick. We have we have a separate upper and lower mantle, but for now we're just going to view it as a single layer. So that's the thickest part of the Earth. The outer core, oh, that was a little typo. Sorry, this 5,000 kilometers, that's supposed to be how deep into the ground it is. Go back to that first diagram. There. So it ends at about 5,000 kilometers. That's what that 5,000 is. There. It is also molten, but it's not as liquidy as the mantle. And then we have the inner core, which is solid rock, and that's about 1,200. Okay, I think that went fairly smoothly. Then we get, I know that this is an interest of some of my grade 8 students. They're wanting to understand how the plates move. So the idea of plate tectonics is that the crust is broken up into multiple pieces. So we have all of these pieces that we refer to as plates, and they're all floating and kind of bobbing on top of the mantle. And each of these moves. So we're going to look at why it moves and then how it moves in different. But they're all, you can think of them as detached from each other, but constantly moving and pushing and pulling away from. Oh yay, all of the little animations work properly. I wasn't sure when I set this up, I wasn't actually sure if it would. I always like to refer to lava lamps when I explain this section. So what drives plate tectonics is the convection currents inside the mantle. So I'm first going to just go to this little diagram and then we'll go back to the. The outer core is very hot, and the outer core will heat the magma in the mantle, and that will cause it to rise. And as it rises, it has nowhere else to go but to diverge and just out. When it is near the crust, it cool, dense again, and sink. And that's where you have the whole little convection current. So that's what this is. I used to have a lava lamp, and I wish I still had one, but a lava lamp was a way of showing this convection current. So it was the same thing, but you had a little light bulb at the bottom, so the lamp part, that little light bulb over here, and because the bulb would get hot, the liquid inside the lava lamp would start to rise, and then when it gets to the top, it would eventually cool and it would sink back down to the sides again. And I actually had, when I was a kid, I had one of these glitter ones. And it was so interesting to watch because I would notice how it would always rise in by the middle, but it would sink around the edges by the glass part. That's where it would sink. So this whole convection current actually made a lot of sense to me when I learned about it in school because I had seen it lava lamp. This little animation, I do just want to apologize to whoever created this animation. I would like to reference it properly, but I have found this on so many different sources that I don't know what is the correct one. But wait, is that way down there? Is that a graphic? Not sure. Yeah, I would like to reference you properly, but I don't know where the original from. Um, but I find it to be a nice visual how the convection currents work. So over here, that's supposed to be the outer core, the red part. You can see it's rising up. It kind of looks like steam almost. So it looks like the steam that's rising up and it's reaching the crust and it's pushing to either side. And as it pushes, it's starting to sink over here. And if you look right there where it's sinking, it's pulling some of the crust down as well. Okay, that is a very important part of plate tectonics because this pushing apart and pulling down at the edges, that is how we get divergent and convergent plate boundaries. And that's also where we get subduction. Tell me if it's too much all at once. Hope it's making sense. I should get a little lava lamp and just have it set up in the back somewhere. Okay, so hopefully this diagram makes more sense now. You've got the heating from the outer core. It rises, the magma rises, it reaches the crust, it spreads out, and it sinks again when it cools. And this just repeats and repeats. And that is what causes the crust to move, or the plates of the crust. So if you look here, this is supposed to be the edge of the plate. Get that right. And this is the edge of another. So this section in between, that is one plate. And this section, that's supposed to. So what is happening is the rising of the magma, of the warmer, lighter magma, is reaching the crust, and it's actually pushing its way through the crust. And as it pushes its way through and it diverges and it moves into the direction, it's a very slow but very powerful movement, which means that it can drag the crust with it. There's so much friction from that convection current that it pulls and it pulls it into opposite direction. And as it pulls it, it can collide into another plate. And that collision is your converging boundary. Now, this is where the density matters. So I mentioned that continental crust is basically light and fluffy, and oceanic crust is dense and thin and heavy. So where we have the continental crust over here meeting the oceanic crust, they're being pushed together by the magma. They're being shoved into opposite direction. But because the oceanic crust is dense, heavier, it sinks under the light crust. So that is where we get this subductions. So because the oceanic crust is denser and heavier, sink down into, go back to this little clip, there you can see it. There it's being pulled down in. So I'm not really going to do, or I wasn't planning on doing volcanoes and earthquakes and all that stuff in the video, but this is where you would see them form. So if you look over here, there you've got some volcanoes diagram. So this is a subduction zone. We've got one form of crust that is subducting under the other, and usually there will be weaknesses or hairs in the crust, and that will allow magma and lava and everything through, and you have little, I say little like they're these small little events, but you have these little earthquakes and volcanoes that start to form. Yeah, well, in the grand scheme of this process, a volcano looks quite tiny. Yes, so you have these lines of volcanoes that would form over there, and you would often experience earthquakes in these areas. You see, they also happen inland, so it's not necessarily where the subduction zone happens. So you can see it over here, it's quite close to the subduction zone, but here it's quite a bit further inland. So it's not necessarily on the plate boundary, but it's often near the plate. So here we'll have a lot of rock that is melting from the oceanic crust, melting and rising and bubbling through the continent. They did also include it. It's not a very big part of this diagram, but over here we have continental crust that is converging with more continental crust. Now, because continental crust is lighter and less dense, it won't sink. And that works fine if it's meeting oceanic crust. But if it's meeting another continental crust and neither of them will sink, you don't get something. Instead, you just get this pile up of fold mountain. So it's just these rocks that keep piling up, holding the old. This is usually the oldest rock feature that we can find. So far, so good. This map of the plate boundaries I like because you can see where the plates are converging and where they're diverging. So you can see that this stay over here. You can see it's diverging over here. So it's moving um, from the east towards the west. And you can see all over here it's diverging, and all over here it is converging, moving in a that way direction. And along the sides, where it's not necessarily moving towards or away from, it's moving in the opposite direction. They're moving parallel. Those are transform boundaries. It's got a so we have divergent boundaries that is separate. We have convergent boundaries, that's when they meet and they collide, and transform boundaries when they move in opposite direction. Sometimes it's not even opposite directions. Sometimes it's just that the one is moving faster than the other. You can almost think of it as a car overtaking another car. They're both moving forwards, but the one is passing them. So that can also be the case. Don't think we see any of that over here. Here's the only what looks like transform boundary, and they're moving in opposite. I have seen it on some maps where they show the arrows pointing in the same direction, and they are just moving faster than. I think we have covered that. Divergent, separating, convergent, combining, transform, uh, moving past. We have different types of divergent planes. The one is where you have oceanic crust diverging, and the other is with continental crust diverging. By the oceanic crust, you would find oceanic ridges. So I'll see if we can find some oceanic. So basically, what happens is the crust moves apart, and it leaves a gap for this magma to through, and it starts bubbling through, and it forms rock over there. Then over here, where you have continental crust diverge, you tend to have these rifts. So the crust pulls away, and it's almost like the remaining rock has no support, so it slumps down, and it creates these rift valleys. Then converging crust. Just a slide. I've definitely missed a slide because I missed the slide where I have converging. There's three different types of converging crust. The one that I have over here is oceanic crust. So you have oceanic means oceanic. They're one of them more subduct, you have a subduct zone, and you get this trench that forms. You will also usually then have some volcanoes like island arcs that form. We'll see if we can find some examples. The other one is where you have oceanic meets continental. Like, yeah, there. There you have oceanic and continental, and because the oceanic is denser, it will subduct. And then the third one, I already explained on the slide, that is the continental, and then you just get a big collision and fall. Just to be clear, it doesn't happen quickly. It's a very slow process. Say big collision like it's a car crash or something. It doesn't happen overnight. And then transform boundaries where they're moving parallel to each other, sometimes in opposite directions, same direction. but you don't usually have features that form over here. So the other two types of boundaries, ridges, you have rift valleys, you have volcanoes, but all these trenches and exciting things form. But by transform plate boundaries, you usually don't have anything that is formed or destroyed, just passing by. Okay, so that was the end of my slides. Is there any questions on the actual material? We go to Google. I hope that this works properly. I know that both have been given. I've changed a few settings. If it doesn't work, then you don't have an alternative. So then I don't know. Okay, so I started over here because there is a nice example of a trench over here. Here we can see we've got the ocean next to North America. So we have oceanic crust and it's meeting continental crust. Something that I did want to point out is that just because ground or land is underwater doesn't necessarily mean oceanic crust. So I want you to notice that it's under the ocean. That is still part of the continental crust. It's just it has been flooded by the ocean. Continental crust isn't whether it's above or below the sea, the ocean. It's a different composition crust. It is thicker, it is older, it is less dense, it is made of different types of rock. So oceanic crust, yes, is underwater, but it has a completely different composition. So it's not oceanic crust just because it's under the ocean. We do get some continental crust that is also. But what I wanted to point out is this dark line, that dark line, that is a trench. So what that means is that the dark blue area, that's my oceanic crust, it is subducting underneath the continental crust, that is light blue. Okay, so that seems to be a little bit clearer. So now this is South America. So you can see that line over there, that is where the trench is. So the oceanic crust is subducting underneath the crust, and you have this deep trench that's. Now, what I want to show you is on the other side of the plate, you'll see where the crust is diverging. So over here, it's converging, and on the other end, diverging. Hello, I see there's a few more people here. Hey, welcome. Hi, I'm good. How are you? Welcome to Geo Cafe. Okay, this is what I wanted to do. The Mid-Atlantic Ridge. So the Mid-Atlantic Ridge is where you have diverging. So diverging, we've got the crust going directions. And you can actually see it with these tiny little fissures. They look like these little tears in the crust. These are actually faults. So they're faults that form when the crust is under stress. But we get to that if we take a look at thing. That is the Mid-Atlantic. Okay, so what happens is because it's diverging, you have magma coming up and it's forming new rock. So if they were to actually check how old the rock is, they would notice that the youngest rock is along the Atlantic Ridge, and the oldest rock is towards the continent. Oh, thanks, Arjun. And the oldest rock is towards the continent. And this is also one of the things that supports the theory of continental drift. Because we can see that new rock is constantly forming and pushing away from the ocean, there's evidence and support to the idea that the continents had slowly dropped. Then we can start wrapping up. Well, thank you very much for joining. I found it interesting. And like I say, I was quite behind on my videos because of the exams the last few weeks, but I want to see if I can try to catch up on a few. Um, I've been wanting to do a few map work videos, but I'm just trying to figure out how to do map work without drawings and diagrams. Because even though that program seems to work, it messes up the videos quite a bit. So I don't know. I'll figure it out. But I'll try to do a few more videos in the next few to make up for some lost time. Is there anything in particular that you would like me to do a video on? Maybe any questions? Well, otherwise, I hope you have a lovely day. And I do believe that it's Father's Day today. So, any dads out there, I hope you're having an amazing day. And I will see you guys again soon. Okay. Enjoy your day. Cheers. Bye.